Hello everyone. So today we will have our last lecture during this year and during this term. Sorry. Hello everyone. Yes, and so there will be some information shared among those who will be invited to the second term of our math club. So there will be also several lectures and several problem sets, but this will be made a little bit later. And today's lecture is a little bit different from the others lectures. So there will be no solutions to the problems that were presented to you, but we will discuss somehow separate, from my point of view, very interesting topic. We will discuss the theorem about representation as a sum of two squares of integer numbers. This theorem usually called Fermat-Christmas theorem because it was somehow published by Fermat. It was not published, but the date was 25th of December, so it's Christmas theorem. And we will discuss several proofs of this theorem. Some of them are very, very simple and elementary, but some of them are quite difficult and have a lot of other applications. So well, this is our plan. I think that today's lecture will be a little bit longer, so I hope that we will cover everything that I have prepared, but maybe if we will have lack of time, I will skip some material. But anyway, please, if you would like to ask something, you could ask in chat. So I mute participants in Zoom, and you could ask your questions in chat, or you could ask your questions in Zoom. I hope that I will have some possibility to check sometimes whether there are some valuable questions or comments. So let's start. This was short introduction just to make people give people time to join us. So I will share my OneNote as usual. So these are the people that will be mainly the main participants of today's lecture. Not all of them are presented here, but some of them at least. So you could guess who is who, but maybe later. So let's start with some preliminary information. So we will discuss the problem about presenting integers as a sum of the squares of other integers. And the first thing I would like to start with that the very, very important formula here, that if you have two numbers and both of them can be represented as a sum of two integers. So for example, n is a square plus b square and m as c square plus d square, then actually the product of these numbers can be also represented as a sum of the squares. This is a very, very beautiful formula. The main idea behind, I think, lies in the topic of complex numbers. So we will discuss complex numbers during the second term a little bit. But here you could think about this formula as somehow a miracle. So I will just write the answer. So it is AC plus BD square plus AD minus BC square. So why is this true? Because when we simplify these expressions, we will see the squares of AC, BD, AD, and BC. And on the right-hand side, the cross products ACBD will disappear, will destroy each other, because here we have plus and here we have minus. But also it's possible to put minus here and plus here. So actually we have maybe somehow more representations here for the product of M and N. So this is a way to get a little bit more representations for the product. So we will use these formulas later, but now we understand that if we have two numbers which can be represented as the sum of the squares, then the product will be also represented. And thus, if we prove that some prime numbers can be represented in such a way, then, okay, we will prove something about their products. So, of course, any square, any perfect square could be represented in such a way. For example, n square is nothing else but n square plus 0 square. So, if we have some even powers of primes in the representation of the number, then of course using our general idea about multiplication, we will get some simplification. So what else? One more thing is very important, will be very important today, that is the following, that if prime number p is of the form 4k plus 1, so it then there exists such number q, that q square plus 1 is divisible by p. So this is not a representation of p as a sum of two squares, but we find two squares such that their sum is divisible by p, and one of them is actually 1. So how can we prove this? There are different approaches for this stuff, but one of the simplest is the following. We could use the Wilson theorem here. So we know that p minus 1 factorial is congruent to minus 1 modulo p. And if we have this, we can write it in the following way. So this is the product of the numbers from 1 to 2k, and then the product of numbers from 2k plus 1 to 4k. So we split it in two halves. And actually, we could say that this is congruent to minus 1, the previous one is congruent to minus 2, and so on. And this is congruent to minus 2k. And since we have even number of minuses here, we find that this is congruent to 2k factorial squared. And thus we see that this formula here, and actually we can take q equal to 2k factorial. Of course, it's better to take q smaller, so we could take as a q the residue of this 2k factorial modulo p on minus residue if it is better. But in this is the finding of this this q will be important for almost all of our future considerations. So if we think about from algorithmic perspective, we look to these problems, we will have to find this Q. And this formula is not so good for finding such kind of number. So because it's very hard to calculate this factorial in terms of P, so it will take quite a lot of time and or quite a lot of memory. So this is a good question, how to find such kind of Q faster. And actually there is some good answer here. Maybe I will give you this answer at the end of the lecture. But now we have just an example of such kind. So the third point I would like, so maybe you have some questions. Please, I will check chat and here and there. So no. So another point I would like to discuss in the preliminary part is the following. So actually I would like to say that if for some a squared plus 1 is divisible by p, and p is prime, and p is greater than 2, then p should be of the form 4k plus 1. So sum of two squares usually is not divisible by p of the form 4k plus 3, except one case that I will tell you a little bit later. So in this case it's not possible. And here I will give some proof that actually will cover the previous part, so the existence of such Q, but it will provide in case of p equal 4k plus 1, but it will not provide the exact example of such Q, so it will be non-constructive. So the idea is the following. So we could consider the following sets of residues. So we take any residue x, which is not 0, modulo p, we assume. We will add to this set minus x, 1 over x. I would like to remind you that we discussed the inverses of the residues, so it's possible to calculate the inverse, and minus 1 over x. So we consider the set of these 4 residues. So usually this set consists of 4 different residues, and this means that we could split all the residues in these groups of 4. But sometimes some of them are coincide. So let us check when this can happen. For example, could it be that x is congruent to minus x modulo p? Of course no, because it means that 2x is divisible by p, and we assume that x is coprime with p, and p is not 2. So this is not possible. So this is never happens. So could it be that x is congruent to 1 over x modulo p? This could be because it means that x squared minus 1 is divisible by p, and this is equivalent to the fact that x is equivalent to either 1 or minus 1. So this is quite simple. So and in this case, if x is 1 or minus 1, we will get a group of 2 residues, 1 and minus 1, and it will collect all of these 4 formulas for x. So this group will consist of 2 residues. And the last one that we should check, the possibility of the congruence x is equal to is congruent to -1/x, and this means that x squared plus 1 is divisible by p, and in this case, of course, we will also we will glue the pairs x and -1/x, and minus x will paired with 1/x. So this means at the same time that this pair, we have this pair, and thus we will also have actually two residues in this group, and others will glue with them. So usually there are four residues in such a group, but there are some special cases when this group can contain only two residues. One of these special cases is 1 and -1, and the other one reflects the situation where when we have such residue that x squared is congruent to -1. So x squared plus 1 is divisible by p. And what we will have at the end of the day, we have p minus 1 residues in total, so it should be split in the groups of 4 plus 1 or 2 groups of 2 elements. So on what that will depends on? It will depends on the residue of p modulo 4. So if p is 4k plus 1, we will have several groups of 4 elements, and we have to have 2 groups of 2 elements. So we will necessarily have this group in case of p equal 4k plus 1. And if p is equal 4k plus 3, we will necessarily we will not have this group. So we will have p minus 1 will have residue 2 modulo 4, and this means that we will have all groups of such kind 4, 4, 4, and one group of 2, which is necessarily 1 and -1, and this group will not exist. So this means that actually a squared plus 1 can have only prime divisors of the form 4k plus 1. Or, of course, it could be divisible by 2. So we will not discuss 2 in our considerations later. So this is the main thing I would like to tell you about this stuff. So do you have any questions here? If no, then I will reformulate a little bit this point. It will be reformulated in the following way. So if we have that sum of the squares is divisible by p, and for example p is 4k plus 3, then it necessarily that a is divisible by p and b is divisible by p. And thus a square plus b square is divisible by p square. So why is this? So if a and b are not divisible by p, so if this these two terms are coprime with p, then it means that a is congruent to minus b square, and we can multiply by 1 over b this congruence, and we will get that a over b square is congruent to -1. And this is not possible due to our considerations, and this means that the only possibility that a is divisible and b is divisible by p, and thus this sum of the squares is divisible by p squared. So what we have at the end of the day? At the end of the day, we have the following, that actually, if you have some number n, which is represented in the following way, so if we have some if we have some prime number of the form 4k plus 3, for example p1, then we know that if this is a squared plus b squared, then it means that a and b should both be divisible by this p1, and then we could reduce this, so we could change alpha 1 by alpha 1 minus 2 and divide everything by p1 squared. So we can reduce this for primes of the form 4k plus 3, and at the end of the day we should get that we reduce all such primes. So any prime of this form should be in the even power in the n. And to understand whether n can be represented as a sum of two squares, the only thing is left behind is the question about, can be this prime represented as a sum of two squares? So if we will have affirmative answer to this question, then we will get that n is represented as a sum of two squares only if all primes of the form 4k plus 3 are represented are in even power in the representation of n. So in this case, we can represent n as a sum of two squares, otherwise not. Because we also, I would like to mention that 2 is sum of two squares here. Yes, and then we could produce the representation using our initial formula. So this is the main question, and this is the question that we are going to answer today, and we are going to discuss several proofs of this fact. So okay, do you have any questions or comments? If no, then let's start. So we will start with one of the simplest proof. I think that it's mainly devoted to Euler, and I think that sometimes this theorem is called Fermat-Euler theorem because I think that Fermat didn't provide the proof of this theorem. Maybe he had his proof, but I think that one of the first proofs was made by Euler, and okay, so this is the main person here, I think, but of course this proof is nowadays a little bit simplified. I think the Euler had maybe not complicated, but too many steps in his proof were presented. So let's start. So we start with the following thing. We can find two numbers a and b such that this is divisible by p. For example, we can take one of them equal to 1 and another one equal to 2k factorial. So I will usually think that p is 2k plus 1. So this will be my main idea. And also I will usually denote q the residue that gives minus 1 modulo p. So this will be our general notation today. So so we can find two squares such that their sum is divisible by p, and both of them are not divisible by p. So now let's reduce them a little bit. So we can choose this a and b in such a way that both of them are smaller than p over 2. So of course, when we just take the residue, we will get the same divisibility, but a and b will be from 1 to p minus 1. But the residues from p over 2 to p minus 1 we can replace by p minus these residues, so they will be smaller than p over 2. So actually, we will usually use this idea that we can take the number with the same residue from minus p over 2 to p over 2. So this is the idea. If this, then this sum will be smaller than p square over 4 plus p square over 4. This is p square over 2, and this means that m will be also smaller than p over 2. So if so, then we could make the following. We could change in this sum of the squares a by some number c, which is congruent to a modulo m, and b by some number d such that b and d are congruent modulo m, and c and d themselves again smaller or equal than m over 2. So again, we can change a and b by their residues modulo m, and if we get something between m over 2 and m, then we can replace them by m minus this residue, and after by this residue minus m. So we will get something between minus m over 2 and 0. And since we have this congruence, we will get that c square plus d square is divisible by m. So we could write it in the following way. So c square plus d square is m times m1, and as above, m1 is smaller than m over 2. So we make the same procedure as for p, but now for m. So we have that the sum of the squares is divisible by m, and then make the reduction. But of course, we lost the main thing, the divisibility by p. But now we will use this beautiful formula that we wrote above. So we multiply these two guys by each other, and this will be p times m1 times m square. And now we write that this is the sum of two squares in a very simple way. So we will take here AD minus BC, I think, square plus AC plus BD square. So we used this formula from the preliminary part, but I choose the signs here in the following way. I choose them in such a way that this is divisible by m. So AD minus BC is divisible by m because A is congruent to C and B is congruent to D. And thus this will be divisible by m squared, and this should be divisible by m squared also because their sum is divisible by m squared. And thus we could divide this equality by m squared and get the following, that AD minus B1 so something goes wrong with streaming. Sure. Yeah, okay, it works. So and thus we get the following equality: a1 square plus b1 square is p m1, and now m1 is smaller than m over 2. So we start with this equality, and we reduce the number m in front of p, and get the same equality for smaller m. So we could repeat this procedure as many times as necessary. At the end of the day, we should get m equal to 1 here. So there are no other possibility. So this is the idea of Euler, how to use this this equation to make the reduction for smaller m's. So this is the idea. So do we have any questions here, or maybe comments? Okay, let's check chat. And no, I see no questions. So then we could switch to the second proof. The second proof is so-called Thue's lemma, the lemma that belongs to mathematician Axel Thue. And this is a quite beautiful idea, and I think that it relates to some other proofs. So I will denote here n is the integer part of square root of p, and I will consider the numbers a and b from 0 to n, and I will consider the list of the following residues. So this will be the list of numbers. So when a and b from this. So I just remind you that q is such residue that q square is congruent to -1 modulo p. So we use the fact that such q exists. And since we have here n plus 1 numbers for variance for A and n plus num variance for B, we have in this list n plus 1 square expressions. And since this is greater than P, we find that two of them will be congruent to each other. Of course, for different pairs of A and B. So we have that A1Q plus B1 is congruent to A2Q plus B2 for some A1, A2, B1, B2, such that the pair of A1, B1 is not the same as the pair of an A2, B2. And this means that A1 minus A2Q is congruent to B2 minus B1. I will square this congruence, and I will get that A1 minus A2 square Q square is congruent to B2 minus B1 square. And Q square is congruent to minus 1. So this is congruent to minus A1 minus A2 square. And thus we get that the sum of two squares is divisible by p. This is not zero, since we have different pairs B1, B2, B1, A1, B1 and A2 by B2, but it's not too big, because the difference between B's is smaller than n, smaller than square root of p, and the difference between A's is also smaller than square root of p. Thus, this guy is smaller than 2p. And the number which is not 0 and smaller than 2p is necessarily p. So we find out that p is equal to this sum of the squares. So this is somehow we find some good values of good residues, quite small, such that they satisfy this congruence. So actually we represent Q as a fraction with a small numerator and denominator. This will relate this idea with the others a little bit. So it looks like a trick, but a lot of other proofs will be somehow similar to this one. So let me ask one more time. Do you have any questions now? If no, then let me continue. The following proof, I call it Dirichlet approximation. It's due to Dirichlet theorem about so-called Diophantine approximation. So mainly it used for the irrational numbers. So this is about how to approximate a rational number using rationals. So it's very beautiful and based on pigeonhole principle. So it's somehow related to the previous one. In Russian, this principle is called also Dirichlet principle. So this is maybe one of the basic ideas behind this theorem. And so I will not discuss this Dirichlet theorem in detail, so you could look somewhere. So there are a lot of resources. So the main name you should put in Google is Dirichlet-Diophantine approximation or something like this. So, but I will express this idea in our terms just to save some time here. So I will look at the fraction q over p, and again I will remind you that q square is congruent to -1 modulo p, and I will start writing the numbers q over p, 2q over p, and so on. And I will calculate these numbers till nq over p. And again, n is the integer part of the square root of p, so-called floor of the square root of p. And I will consider all these numbers modular 1. So I will do the following. I will draw a circle of length 1, so and start at some point which I call 0, and then I will draw here the point, maybe it's better to draw it in other direction, in positive direction. Q over p, it is smaller than 1, then 2q over p, it may be smaller than 1, and so on. I will draw these points. Maybe when I go till nq over p, I will make several turns around this circle. I would remind you that the length of the circle is 1, so I'm considering this numbers modulo 1 actually. But at the end of the day, starting with 0 times q over p, I will have n plus 1 points on the circle. And thus, it means that there will be 2 points close to each other. There will be some kq over p and lq over p such that the difference between them is smaller than 1 over n plus 1. So I would like to write it in the following way, that kq over p minus lq over p is smaller than 1 over n plus 1, but it's not true because they could appear on different turns of our rotation, so it's up to integer, up to some integer. I should add some or subtract some integer here, and I will get this equation. So here I will denote k minus l by m prime, and I will assume that k is greater than l, and this m prime will be smaller than n, smaller or equal than n. So finally we get the following, that we find two numbers m prime and m such that this guy is smaller than 1 over n plus 1, and we know that m prime is smaller than n also. So, okay, and you see that we somehow approximate q here. Yes, so this is again some idea that was in the Thue lemma. So there we were approximating number q by some fraction, and here we also make some approximation with which is related this square root of -1 in modulo p. So what will I do here? I will write the following. So this is smaller than 1 over square root of p, and then I will multiply by p this stuff, so it will be m prime q minus mp square is smaller than p, I think I will get, yes? So I multiplied by p and squared this, and I will add here m prime square. Minus mp so m prime is smaller than square root of p, so this will be smaller than p. All of this will be smaller than 2p. And I could see that this guy is congruent to what? It's congruent to m prime square plus m prime square q square, since this is divisible by p, and q square is minus 1, so this is congruent to 0. So this number is divisible by p again, and of course it's not 0, and it's smaller than 2p. So that's it. We get that p is actually equal to this, and we have the representation. And again, we have the representation with the following form. One of the guys is something multiplied by q, and maybe with some p's there, and the other term of this kind. We will have such kind of stuff in the later proofs also. So this is the idea that I call Dirichlet approximation. Do you have any questions about this? Okay, I can't see any questions in chat. So let's continue. Now we are ready for the very, very beautiful proof of Don Zagier. This proof appeared in 1919, so it's almost 35 years ago. So, but later it was there were a lot of works later for understanding of this proof. So the work of Zagier was named one-sentence proof of Fermat theorem, and it was one-sentence proof. But it was very short work. But it was somehow again some miracle which was not so understandable, and there was some involution involved. So there was some ideas behind, but it was not clear for many people. But since that time, there were a lot of works that were trying to represent this work of Zagier in another way. So to understand how we could look to this this idea. I will not go into the details of this proof, but the beautiful idea of Spivak is the following, that so I will start with the beginning. So the idea of Zagier is the following. Let us consider the equation of the following way. So it will be, I will represent P as x squared plus 4yz. Of course, x, y, and z are positive integers. So So, from one side, we could understand the following, that actually any representation of such kind can be mapped to the other representation in a very simple way. We could just replace y by z and z by y. So we could pair all such kind of representation. So in general, it should be even number of such representations. But it could happen that in one of these representations, y equal to z, then the number of representations will be odd. So everything will be paired except one, where y is equal to z. And, or maybe, it could be, if there will be odd number of representations, then there should be such. Maybe there will be several representations of such kind, but if, maybe I should write it in the opposite way. So if the number of representations is odd, then there exist such where y is equal to z. So, and now we will find another way of pairing between representations. So we draw a square x times x and draw 4 rectangles y times z. And then we will replace this by another square, so we could cut this here, 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 and here, and get another representations of such kind. So it will be, I will draw schematically. So we have something like this. So these are equal rectangles, and we increase the square and get another representation. And vice versa, if we have such kind of representation, we could reduce it to the another one. So, and it could be written in direct formulas and check that it works. And the only representation that don't have pair in such pairing is the following one. So we take x equal to 1 and add such kind of rectangles. So here we have, of course, p minus 1 over 4 cells. So, and at the end of the day, we have some pairings and one representation that has no pair, and thus the total number is odd. And this means that in these pairings, also someone doesn't have a pair, and this gives us representation as a sum of two squares. So this is a very impressive, I think, and very beautiful proof and very beautiful idea how to represent it as squares and rectangles. There are some technical, not difficulties, but it should be written accurately that actually everything works here, and so, but it's quite easy to recover all the details. Okay, do you have any questions about this proof? Let me check YouTube. There are no questions. Okay, then we are ready to switch to maybe see some questions here in chat. No questions here. We're ready to switch to more complicated proofs, and I think that ideas behind these proofs are much more, I would say, important for different areas of mathematics. So if you have some proof which is something like a trick, actually usually it doesn't give inspiration for something. But if you have studied something and get as a path result, for example, this theorem, then it appears that you have some theory in which your result is included. So the proof of Zagier, I think it's a little bit separate. So there were some understandings afterwards how it works. And of course, there were some inspirations before. So there were some works before from which I think Zagier got his proof. But anyway, I think that the proofs that I'm going to present now, they are more about mathematics. So it's about how it works. So one of the proof is I'm not sure that this is Minkovski proof, but maybe someone used his theorem. I'm not sure. I don't remember. But it's very, very beautiful and again geometric idea here. So the Minkovski theorem is the following theorem. I will formulate it in on the plane because we will work on the plane, but it's more general. It's about bodies in multidimensional spaces. So let us consider figure phi. It's centrally symmetric with respect to origin. Convex figure with area greater than 4. Or maybe exactly 4. It's 4 maybe enough. No, let it be greater than 4. Then, so we have 0 point. We have some figure which is centrally symmetric, and the area of this figure is greater than 4. Then there exists at least one integer point in phi except origin. What is integer point? Is a point with integer coordinates. So I would say that if you would like, I can write it as z square, and the intersection with phi will not coincide with the point 0, 0. It should contain at least one more, and of course it will contain at least 2 points, because if we have some point, we have symmetric one also in our set. So there are different proofs of this theorem. I will provide maybe two. No, one as idea is just an idea, and the second a little bit more maybe understandable, more elementary. So the one is the following. So we will consider the figure phi over 2. So we make a scaling with factor 1 over 2 with this figure. Then the area of this figure will be greater than 1, and it will be still centered at point 0. And we make a copies of this figure centered at any integer point. So we draw this figure centered at any integer point. And it happens that some of these figures should necessarily intersect with each other. And if we have figures which intersect with each other, due to their convexity, we will find that the midpoint between these two centers should be inside this figure. And then we make scaling back and get that this midpoint will become an integer point inside the figure. So why some of these two figures placed in each integer point should intersect? Each of these figures has area greater than 1. So when we will look at the plane, at the big part of the plane, we will get that we placed figure with area greater than 1 at each point. And the area of this big figure is approximately the number of integer points. And since the figure phi over 2 has area greater than 1, then by pigeonhole principle, we will have some intersection in this approximation. So this is an idea, but it could be made accurate. So this could be done. So this is the idea why it is true, and one of the proofs is based on this. But another idea is the following. So let us consider this figure phi over 2 and cut it by our lattice. So there will be some parts of the figure in the different cells. We will take these parts from the different cells and collect in one cell. And if we collect this part in one cell, we will find out that since the total area of these parts is greater than 1, one of the points is covered at least twice. So what does it mean? It means that in our figure phi over 2, we have 2 points which can be connected by vector with integer coordinates. So when we place these parts in one cell, it means that we shift one part by integer vector, and then it appears that they have intersection point. So this means that the copies of this point in these two parts differs on vector with integer points. So finally, at the end, we will find that there are 2 points inside our figure phi over 2 such that this vector has integer coordinates. Now we will take the origin and we will reflect one of these points by this origin. And we will have that this vector we will find that this vector has semi-integer coordinates. So this is the midline of this triangle. All this stuff is inside figure phi over 2, and this vector is semi-integer. So its coordinates is integers divided by 2. Now we scale back twice, and we will get that this point will go to the integer point inside figure phi. So this is the Minkovski theorem. Do you have any questions about the proof of this theorem, or maybe some other questions? If no, then we'll use this theorem now. And it's somehow also an important thing. So it's very interesting how such kind of theorem could help in our considerations. The idea that we will explore now, and actually we will explore this in some later proofs also, we will consider the following function of following type. It will be ax squared plus 2bxy plus c y squared. So this is a quadratic function on a plane. And sorry, let me check. Somebody is writing something. So this is a quadratic function, and if so it has very similar things to quadratic function of one variable, and the reason is that if we divide by y squared, it will be a quadratic function of x over y. So so it has the same stuff like discriminant or something like this, and so on. So it appears that if b squared minus ac, so this is quarter of the discriminant, if it's smaller than 0, then the lines f of xy equal to something, for example to 1, are ellipses. And it's not hard to check, and I think that this will be a good exercise for you, that if we consider this equation, then this ellipse bound a figure of area. No, I think that we should consider of equal to equal to 1, then the area that is bounded by this figure is what? So, for example, if b is equal to 0 and a equal to c, it will be just a circle already 1 over square root of a. So, okay, if b square minus ac is equal to -1, then area bounded by this figure will be 2 pi. Not 2 pi, it will be pi. Pi. Yeah. So the main example here is b equal to 0 and a equal to 1, equal to c equal to 1. Then it will be a circle, and its area will be pi. So, and if we consider the figure f of xy is smaller than 2, then area of this figure is equal to 2 pi, and this is greater than 4. So this will be ellipse of the area greater than 4. And thus it means then that in this figure there should be integer point necessarily. So this figure is symmetric with respect to a region, so it will be ellipse symmetric with respect to a region, and its area is greater than 4, so there should be integer point. At this integer point, the value, of course, should be integer. If a, b, c are integer, for example, then value should be integer. And then since it's smaller than 2, it should be 1. Then we will find the point such that this guy is equal to 1. So there will exist. And this will give us the desired equality for P. How it will be? I will take C equal Q square plus 1 over P. So Q is the residue that gives square root gives residue minus 1. A I will take equal to P, and B equal to Q. So it will be the following. It will be Px square plus 2qxy plus q square plus 1 over p, y square equal to 1. I will get that there exists integer point that gives us this. And what should we do? We should multiply this by p. It will give us p square x square plus 2qpxy plus q square y square plus y square. And this is a perfect square. So this is px plus qy square. And this is the representation of P. So the idea of behind the using of theorem of Minkovski is to find the solution for such equation with some integer x and y. So, do you have any questions at this point? And again, I think that we already had such kind of representation somewhere here. Yes, for example, in case of usage of Dirichlet, it was almost the same structure of the answer. And we will get the same structure of the answer a little bit later in Lagrange proof and maybe in this proof. So this proof I studied yesterday from Fedor Petrov's comment. So he told me that there is some idea of usage of somehow inverse Cauchy-Schwarz inequality, and this gives us the necessary information for proving the Christmas theorem. So how it will be a little bit similar to the previous considerations, but it will be different somehow. So what should we do? Again, we will start with the following fact, which is of separate interest actually. So let us consider ABC positive integer. So and let us assume that AC minus B square is greater than 0. So you see here again the discriminant somehow yes, and it's negative. So in our case it was -1, and it will be the same in our situation. So we will use somehow this quadratic expression in this proof. So we start with this, and then it happens that there necessarily should exist two vectors x and y in some space Rn such that the square of the length of x is exactly a, square of the length of y is exactly c, and their scalar product is x is exactly b. So here it is not necessary to know what is Rn, what is length here, and scalar product. You could just write that A is sum of the squares of some xj's, B is sum, C is sum of the squares of some yj's, and B is sum of xj, yj. And this inequality is just the inequality that sum of the squares of xj's times sum of the squares of yj's is greater than sum of xj, yj. So this is Cauchy-Schwarz inequality. What do I mean by inverse Cauchy-Schwarz inequality? So we have some expressions of such kind with integer a, b, and c, And then it is possible to construct vectors that represent these three guys, A, B, and C. So that give us such kind of expression. So now we will actually switch a little bit back to the functions and to the discriminants. So what does it mean, this inequality in terms of discriminants? We can consider the function f, which is at squared plus 2bt plus c. Then what is written here, that b squared minus ac is discriminant over 4 is less or equal than 0. So this polynomial is greater than 0. And what what we can say from this, that it can be represented as a sum of the squares. So this is equal, if we have these formulas, to the following stuff: xj t plus yj square sum from j to n. So it's very easy, because some of the squares here will give us a. The cross products here will give us 2b, and the squares of y's will give us c. So these formulas is exactly the representation of this quadratic polynomial by sum of the squares of the linear polynomials, but with integer coefficients. So how can we prove the existence of such representation, or existence of such vectors x and y? So there, the proof is a little bit tricky, but it consists only of 2 steps, I think. So it's quite easy. So first of all, in case b is smaller than a and smaller than c, so it's the smallest coefficient here, this representation can be given explicitly. So in this case, we can just take this linear path from here and represent it as t plus 1 square. So I will just write the following, that f of t is b times t plus 1 square. So I compensate this stuff here, plus a minus b times t square. So now I compensate this, and c minus b 1 square. So we should take b b times this linear function t plus 1, a minus b times linear function t, and c minus b times linear function 1. And then we will get this representation. So it's quite simple here. So, and we use that this is greater than 0 and this is greater than 0, and integer, of course. So if we have something like this, that b is greater than a, then actually we could reduce b by a just by shifting f. So if f can be represented in such a way, then of course any shifts can be represented, and vice versa. If we can make some shift in t and find representation, then we could make shift back and find the representation. So if b is greater than a, then I propose to put part of this stuff inside first inside the square. So I will consider f of t minus 1. So it will be a times t minus 1 square plus 2b times t minus 1 plus c, and it will be the following. So it will be at square plus 2 times b minus at plus something like a minus 2b plus c. So you see that here we get smaller number now in front of t, and of course we get some non-negative coefficients here. So this will be non-negative because this is just a value at point t equal to 0, and it should be non-negative for non-negative function. So, and now we should represent this function as a sum of the squares of linear functions, and we could make this reduction till the time when b minus a will become smaller than a. And so what is the correct way to say something here? We could at the beginning take assume the contrary and take the smallest b that do not satisfy the condition. Then if it is of such kind, then it's not true, and if it's of such kind, then we could make it smaller. So then we will have finally this representation. So okay, how we can use this representation now? So as I said, the quadratic function of such kind is a very natural thing for Fermat theorem, and I will just put this a, b, and so I will write some equation. Yes, so I know that there are some numbers that satisfy this equality. Then I could just take b equal to q, c equal to p, and a equal to a. And this means that ac minus b square is 1. So discriminant is negative as we wish. And then I will just make some manipulations with this stuff. So now I know that a is sum of xj's. I will write until n minus 1 plus xn square. And b is sum of xj yj plus xn minus 1 yn xn yn. And c is sum of yj square Yes, and now I will write some inequality. So if I consider a minus x, I will assume that yn is not 0. So I will choose I will rearrange them in such a way that yn is not 0 here. So I will write the following. So this is the sum of the squares of these guys. And this is the sum of the squares of these guys. And this is the square of this. So this is greater than 0. So this is again Cauchy-Schwarz inequality, but I rewrite it in a little bit another way, just for this for these parts. So now I will simplify this. So now I will need nothing from others x's here. So and finally I will find actually this this formula. So let's see what is written here. So we have AC minus B square here, which is 1. Minus A by n square minus C xn square plus xn square yn square, which will disappear after this, and here it will be 2b x1 xn yn. So this is 1. Yes. So now I can multiply by p this, and I will get the following. So p minus ap, which is q square plus 1, yn square minus c p xn square. C is p, yes, so it will be p square here. And b is q, so it will be plus 2q p xn yn. And we see that here we get that this, also this is not quality, we multiply by p. So here we have that p minus q by n minus pxn square minus yn square. So we get that this is greater than 0, but of course it's smaller than p, because strictly smaller than p, because yn is not 0 here. And this is divisible by p because here we take the integer stuff and multiply it by p. So this is divisible by p. And smaller than p, then it's 0. So it should be 0, and thus p is represented as the sum of the squares. And you see that we get the same expression as above, actually. And actually we used the same quadratic function as it was in Minkovski proof. So this is the proof with inverse inequality, Cauchy-Schwarz inequality. Do you have any questions? So now I will give very short proof, but actually it will not be a proof because the main theorem will be left behind. I'm not sure that this is the Dedekind proof, but I found this information somewhere that there were 2 proofs by Dedekind using Gauss numbers. What are the Gauss numbers? Gauss numbers are so-called integer complex numbers. They are the numbers of the form a plus bi, where I is square root of -1, and a and b are integer. So sometimes this, not sometimes, this usually denotes by z of I. And these numbers have the same properties as usual numbers have. We can multiply these numbers, we can add them and subtract them. So they almost like integer numbers, so there are no difficulty. We can say what means that one number is divisible by another one. It means that there is some number from this set such that multiplication gives us the result. And so we can define divisibility, and it occurs that actually the same theorems that in integers are true, so any number can be represented as a product of primes up to rearrangement and multiplication by some numbers that play the role of 1 and minus 1. In our case, it will be the divisors of 1, so it will be 1, minus 1, I, and minus I. And if we take this information into account, so there will be divisibility with the residue, so we have some order on these numbers. We can add the notion of the norm of Gauss number, and so on. So we'll get the same structure, the same bucket of facts that we usually use for integer numbers. We discussed this a little bit during our previous lectures. So the ideas from integer numbers somehow could be replaced, could be moved to the polynomials, and could be moved to these numbers also. And if we believe in in the fact that arithmetics in this set of numbers is almost the same, then what we will get? We will get the following, that q squared plus 1 is of course divisible by p, so it could be represented as pm, as we discussed. At the same time, if we consider this equation in this set, we will get that this can be presented in another way. And what we see here, that none of these two numbers is divisible by p. So it's not possible that this is divisible by p. Because if we multiply p by a plus bi by some Gaussian number, then of course we can't get this I at the end. So the coefficient 1 in front of the I is not possible to get as a product of p and b. So it's not divisible by p. And q minus I is also not divisible by p. So it means that p is not prime in these numbers. So we know that if product is divisible by some prime, then one of the factors should be divisible by this prime. And this means that p is not prime. But what does it mean? It means that p can be represented as a product of two Gauss numbers. So and this means that actually we could calculate the norm of this, or multiply by the conjugate. So conjugate here will be the same number as p. Conjugate here will be a minus bi and c minus di. We can multiply by this, and we'll get that p squared is a squared plus b squared times c squared plus d squared. And these are integer numbers, they are no complex numbers anymore. So this means that the only way to write this, if this was not 1 or I or minus 1, that this is p times p, no other way. And this means that a squared plus b squared is p, and c squared plus d squared is also p. So this is a very, very short proof, but behind this proof is a great theory. You should somehow know something about complex numbers, not too much. We will cover this during our second term, so we will discuss complex numbers a little bit. But Gaussian numbers we will not cover, I think, but all ideas that we use for integer numbers are valid for those numbers and can be proved almost in the same way. So there are no difference. Okay. Do you have any questions to this part? If not, then let's go further. Next proof is Lagrange proof. I think that this is Lagrange proof. I hope that it's difficult. And again, there will be some fact that I will not prove. So it's the main tool Lagrange used to prove this theorem, and again it gives a lot of information in addition, so there was a lot of stuff to study after this. So the idea of this proof is to consider the quadratic forms, and we already considered them. So what is the quadratic form? The quadratic form is the following stuff. I will write right now b without 2 here, so it will be of such kind, and I will consider again a, b, and c integer numbers. And what can we do with these quadratic forms? We can change the variables in one of them and get another, and try to change them back. And what kind of changes of variables? We will consider the linear change of variables. So we will consider such kind of change of variables. X prime is alpha x plus beta y, and y prime is delta x plus gamma x plus delta y, and vice versa. So they should be, we should have possibility to return back to solve this equation and find that x is something like alpha prime x prime plus beta prime y prime, and y is gamma prime x prime plus delta prime y prime. So we can solve this equation. But if we consider in integer numbers x, y, x prime, and y prime, and working with integer numbers, if we think that this manipulation with x and y save this property to be integer, it means that it restricts alpha, beta, gamma, and delta. And how it restricts? Actually, it appears that it should be alpha delta minus beta gamma equal to plus minus 1. And what is the idea of Lagrange? The idea of Lagrange is, of course, multiplying by minus 1, it's not interesting at all. So the idea of Lagrange is to say that two forms are equivalent if they can be, one can be obtained from another by such kind of change of variables. So we could make substitution, for example, these guys insert in this form and get another coefficients for x prime and y prime, and we will call that these two forms are equivalent. And it appears that, of course, some properties of the form are saved when we make such kind of transformation. But the main thing that Lagrange understand that if the discriminant of the form, which is b squared minus 4ac, is equal to minus 4, then all such forms are equivalent to each other. And this means that actually they have the same list of values at integer points. Because if we have some value for one form, then after transformation, we will get the same list of values for the equivalent form. So this kind of transformations will preserve preserve us the list of the integer values, of values at the integer points. So, one of such forms with discriminant minus 4 is x squared plus y squared. And we would like to understand that p that equal to 4k plus 1 is among the values of this form at integer points. And we will construct another form with discriminant minus 4 with value p among its values at integer points. And actually, we already constructed this form twice in the proof of Minkovski and in proof with inverse Cauchy-Schwarz inequality. So I will just write this this form. So it should be something like px squared plus 2qxy plus q squared plus 1 over p y squared. So this is integer number, yes, q squared plus 1 is divisible by p, and this form is equal to p at point 1, 0, so p is among its values. And what is the discriminant of this form? It's q squared, 2q squared, minus 4 times p times q squared plus 1 over p, and it's exactly minus 4. So we find quadratic form with discriminant minus 4 with value p. And since Lagrange proof theorem that all forms of with discriminant minus 4 are equivalent, then we have that this form should have this value in integer point. And from my point of view, this is a very beautiful idea. And of course, after that, we could study different stuff. We could study the numbers that are represented not as a sum of the squares, but as a sum of, I don't know, x squared plus 5y squared. So, of course, there will be different discriminant, and we should understand what forms are equivalent with this discriminant. So we should study a lot these quadratic forms, and this was the part of the work of Lagrange. And Lagrange actually proved quite many theorems related to the sum of the squares, different from this one. So this his effort was quite huge here. And of course, we could consider not only quadratic forms with 2 variables, but we can consider quadratic forms with 3 variables and 4 variables and so on. So it's it gives a lot of ideas additional to the field, and this is I think very important. But of course, we are not able to prove that all right now that all forms with discriminant minus 4 are equivalent. So this is the gap as in case of Gauss numbers. Okay, do you have any questions here? So if no, then let us go to the last proof, maybe. So it's I will not provide the details here. So there are there are different approaches with continuous fractions to prove the Fermat theorem. When I was a high school student, I studied different approach from those. From that, I will tell you today. So there was some, I think, difficult ideas, and as I remember, these ideas can be found in the book of Hinchin about continuous fractions. But when I was preparing to this lecture, I found out that there are different approaches now using continuous fractions. And from some of the works, I understand that actually the proof of Zagier is somehow related to these ideas of continuous fractions. So the manipulation that Zagier bring to his proof somehow inspired by work with continuous fraction. And the same will be about the algorithmic part, the last proof and the last not proof thing during this lecture. But what is the continuous fraction? The continuous fraction is the following stuff. So we take some integer numbers and put in them in following way. So there will be the list of n integer numbers will give us such big fraction. For example, so this I will denote in the following way: a1, a2, etc., an. So for example, a1 over a plus 1 over b is something like b over ab plus 1. So this is the fraction with two elements ab. So this fraction we will write as a normal fraction Pn over Qn. And actually there is a recursive formula for Pn's and Qn's, and there are a lot of stuff about this continuous fraction, and all this stuff can be proved using induction actually. So there are no big ideas. So usually, so when we considering such kind of fractions, you will get that the numerator and denominator of this fraction will be coprime, so there will be no possibility to reduce this fraction. These fractions are very related to best approximations of some stuff. So when we cut the fraction at some point, then we will get somehow best approximation of the number, and this gives some ideas. So make some bridges between this and the Dirichlet approximation theorem and lemma Thue, maybe somehow related to this, and so on. But what is the main effort here? So how could it help to prove the theorem? So there are several points that can be proved by induction, and at the end of the day they will give us the representation of P. So first of all, I will denote Qn I will write the following way in such kind of brackets: a1, a2, etc., an. So this is the denominator of this fraction. There are some formulas for this qn's. So again, there is a recursive formula for them, and it gives a lot of information. This recursive formula is the following: that qn is equal to an qn minus 1 plus qn minus 2. So one beautiful thing is the following, that if we write these a's in the in the opposite order, then we will get a fraction with the same denominator. So if I consider the continuous fraction an minus 1, etc., a1, it will give me another numerator, but the denominator will be the same. For example, in this case, if I consider the opposite order, I will get something like a over ab plus 1. So the denominator will be the same and the numerator will be different. So it's general for all type of fractions of such kind. So we have such kind of recursive formula. It's the clue to all the properties. And one more property is the following. Let us consider the following idea. We will try to cut this denominator, this fraction, in two parts and calculate the denominator using these parts. For example, one of the way to cut is the following: to cut this, calculate this stuff, and then add this back. So we cut somewhere, and then it appears that the denominator can be calculated in the following way. We could split at this point. Just will be the product of these guys, as I remember, and we should add the following. We should eliminate these guys here, am plus 2, etc. am. So actually, this is one of the cases of this formula. So it could be proved using this formula, and this is one of the special cases. And now the main idea is the following. Let us consider, guys, 1 over p, 2 over p, etc., p minus 1 over 2 over p. So the first half of the residues, and consider their continuous fractions. And it will appear that all these continuous fractions could be split into pairs. So since they have the same denominator, we could consider to each of them corresponds some sequence, and then we could revert it. So consider the opposite order, and if this relates to some fraction with denominator p, the other one will also relate to some fraction with denominator p, and so we will get some pairing here. And if p is 4k plus 1, then we get that what should we get here? Maybe something should be avoided. I think that we should start from maybe from 2 over p. Yes, I think that I should delete this one. I don't remember exactly. So in this case, they will be split into pairs, except one fraction that will correspond to itself. And it means that its fraction is symmetric. So it will be of the following structure: A1, A2, something else, A2, A1. And if we split it using this rule at the middle of this stuff, there will be 2 possibilities if there are odd number of a's and even number of a's. In one case, we'll get that this means that p is not prime. So actually, 2 guys here will just coincide to each other, and we will have big factor of some factor of p. And in other case, we will get here exactly square here and square here. And thus, p will be a sum of 2 squares. And this will be the result. So this is, so it's quite tricky proof. And I think that details you could find in the internet, maybe. But it, as I understand, some of such ideas provide another ideas as usual, how to find the representation, and based on the ideas that we have in this continuous fraction, it is possible to somehow find a good algorithm. And this is the last thing I would like to discuss. So first of all, as I said, one of the questions is how to find Q. So this is a usual problem when you want to find the representation of P. One of the steps is to find Q, or it could be a separate question, how to find the square root of -1, or square root of any other residue if you have such question. And this is very important for cryptography. So this is one of the most important questions for big primes, how it could be done. Of course, you could just take one residue after another and try to find this. But the answer is the following, that actually all residues among 1 to p minus 1 can be split into 2 groups, so-called quadratic residues and quadratic non-residues. So quadratic residues are those that can be represented as x square. So this residue is such residue that there exists x such that x square is congruent to r, and here should be non-existence. So we will discuss during second term how many such residues there are, and it appears that exactly half of the residues are quadratic and half of them are non-quadratic. If we have quadratic residue, then if we calculate the power p minus 1 over 2 of this congruence, we'll get that x to the power p minus 1 is congruent to r to the power p minus 1 over 2. And x to the power p minus 1 is congruent to 1. So we get that for quadratic residues, this guy is congruent to 1. And for non-quadratic residues, if R is non-quadratic, it happens that R to the power p minus 2 or 1 over 2 is congruent to minus 1. So actually, when you calculate R to the power p minus 1 over 2, it should be 1 or minus 1, because squared it will give exactly 1. So, and this is the difference between quadratic residues and non-residues, and this is the Euler test or Euler property or something like this. Euler condition, I think, for being non-residue. So if we take non-residue, we could have this one, and then r to the power p minus 1 over 4 can be taken as a q. And for calculating the powers, there is a very good algorithms to do this, especially modulo p, because you could write the p minus 1 over 4 in as a sum of powers of 2, and then use squarings to calculate this power, and this is quite fast. So now how we could find non-residue? It's a question, but the answer is quite simple. One of the ways is just to randomly choose residues and check them where they quadratic or not, just calculating these powers. And since with probability 1 over half we get non-residue, then it's okay. So it could be, it works not so bad. But the other way is to take the prime numbers starting from 2 and check them if they are residues or non-residues. And the answer is the following. There is a law to check this quadratic reciprocity law. This is a way to check whether primes are quadratic residuals modulo other primes or not. And it's quite simple to understand this. And actually, it appears that the first non-residue, the number of the first non-residue, will be smaller than something like p log, something like, I should check. Square root of p times log p. So so you will find it quite fast, but actually there is a theorem that if somehow some extended version of Riemann hypothesis is true, then n of p will be smaller than log p squared. But in practice, people who use this algorithm they tell that it's much more smaller than log p squared. So you will find this non-residue in the beginning, actually. So there will be no problem. So you will just check 2, 3, 5, 7, and so on, and it will be okay. So you will find non-residue among first several numbers, most highly likely. And this will give you very fast algorithm to find this Q. Not very fast, but faster than others. And this is very important. And now the tricky question is how to find the sum of the squares that equal to P. And here the algorithm that is called, as I remember, Hermitte-Serret algorithm. And actually, this is the 10th proof of the existence of representation, but I have no time to show you this proof. It's the following. You could take P, you find Q, and you should start the Euclidean algorithm. So I will write that P is Q times M1 plus R1. Then I divide Q by R1. So I will get R1 M2 plus R2. So general Euclidean algorithm. And of course, these residues decrease. And at some point, we will get two residues which are smaller than square root of P. And the main trick here that sum of these squares will give you P. It's very, very beautiful result and very beautiful algorithm to find this sum of the squares. And I think that this is a good place to end our lecture. So do you have any questions? I think that maybe I could switch on. If you want to ask the question, not in chat, but not another way. So if there are no questions, I hope that this lecture was interesting and it was you understood something. Most of the topics, some of the topics we will cover during our second term, so we will discuss something. And yes, there will be notifications about next term. So the first lecture will be on January 11. And I think that you will get invitations to Cognitera and to Discord channels, I think. And so I think that all these notifications, invitations will be sent before New Year, I hope, but maybe there will be some technical issues, then it will be later. Yes, but I think that almost everyone from today's who is here, as I remember. No, I can't guarantee, but yes.
Excuse me, can I ask a question?
Yeah.
When will be the next lesson?
The next lecture will be on January 11.
Thank you.
Okay, if there are no more questions, then no, you have no problems till January 11. You have vacations. Yes, you could think about this lecture and try to answer some questions here that were raised. I think that there are a lot of stuff to think about, especially about algorithms. It's very interesting. So yes, then have a nice vacation, have a nice New Year, and have a nice rest of this year. Thank you very much. Bye bye.
Have nice holidays. Bye.